In chapter 13 and 14, we encounter two types of equilibrium problems. One type where we use concentrations or other quantities to find K, and of course the other type where we use K to find concentrations with Rice table. Well, guess what, folks? The problems involving Ksp are the same, with the same assumptions for K values like we saw before, and of course, one big assumption that we use for solubility problems, which is that we assume complete dissociation for those slightly soluble compounds to their aqueous ion. So that assumption of complete dissociation is very important because guess what? It's because of this assumption that all of our calculations involving Ksp can only be approximate values. And so naturally folks might say, well, why? Well, the answer is complicated and you will need physical or analytical chemistry for a full picture, but to sum it up, a lot of slightly soluble salts have polar covalent or metal non-metal bonds that end up having partially dissociated or even undissociated species that could be a part of the overall equilibrium portion. And guess what? It can affect solubility and accuracy of a lot of our labs and therefore our approximations. And so again, we look at everything as an approximation with these calculations. But we still are going to move forward and learn how to calculate Ksp just like we did in 13 and 14 with those two specific ways. Okay, so let's focus on the meaning of Ksp and how to determine it from solubility values. The Ksp value indicates how far the dissolution proceeds at equilibrium or saturation. And we usually will be given Ksp values just like you see in this table here of these common values at 25 degrees Celsius. So for example, if we were using aluminum hydroxide in calculation, you will be given the Ksp value of 3 times 10 to the negative 34. Most of the time you will not be given a dissolution reaction, so you would need to know how to dissolve these particular solids into their aqueous ion. Now the Ksp expression is going to quantify the extent of solubility. How does it do that? By expressing the equilibrium concentrations of those aqueous ions, okay folks? And we have that cation and the anion. And of course, they're going to be in a saturated solution because they're in equilibrium. Now these concentrations are directly related to a new term we're going to bring in, which is molar solubility. So what is molar solubility? Before we focus on molar solubility, let's talk about solubility in general. Now, solubility is the measure of how much a substance can dissolve in a given solvent, okay, folks? And it usually has the units of grams per liter or grams per milliliter. Now, if we want to focus on the molar solubility, all we would do is convert our units of grams per liter to units of molarity, which is moles per liter. So you would simply need the molar mass to go from grams to moles in order to get molar solubility. So now molar solubility is going to represent the maximum amount of solute that can dissolve per unit volume in that solution, just by simply converting it to those molarity units. Okay, folks? So let's get down to question types. The first type of question, you have to find Ksp. A lot of times you might be given molar solubility so that you can get the concentrations of your aqueous ions and then use that and of course a balanced chemical equation in equilibrium to get our Ksp expression. The second type of question is that you'll be given a Ksp value in some concentrations and you have to use those in a Rice table to help you solve for solubility or of course molar solubility. Now our X value on the Rice table is actually going to equal our molar solubility because that's actually equal to our concentrations here in equilibrium of our aqueous ion. And if we get our molar solubility in moles per liter, we can then convert moles per liter back to grams per milliliter or even grams per liter, depending on whatever the question asks. So let's go back to the Avengers compound for some examples. All right, folks, we're back at the compound for an example. Remember to create and build a strategy to approach problems for yourself. So this says determine Ksp from solubility. For letter A, it says you have lead 2 sulfate. They already gave us the formula here. Is a key component in a lead acid car battery. Its solubility in water at 25 degrees Celsius is 4.25 times 10 to the negative 3 grams per 100 milliliters of solution. What is the Ksp of PbSO4? That's the first. Letter B says when lead 2 fluoride, which is the formula here, is shaken with pure water at 25 degrees Celsius, the solubility is found to be 0.64 grams per liter. Calculate the Ksp of PbF2. So let's talk. We need Ksp. Therefore, we need Ksp expression. In order to get a Ksp expression, you need a balanced dissolution equation, right? Once we have our balanced dissolution equation, then we have to look at the question and say, what else did they give us? They gave us the solubility of both of these compounds here. And so since we have the solubility, we can convert those units to molarity to get what? The molar solubility. And of course, the molar solubility is directly connected to the Ksp expression. Okay, so for letter A, we have PbSO4 solid, which is going to be in equilibrium to slightly dissolve into Pb2 plus and SO4 2 minus ion. The Ksp expression is Pb2 plus and SO4 2 minus multiplied by one another, of course, their concentration. They gave us the solubility, and sometimes you'll see solubility as this kind of capital S shape here, and it's going to equal to 4.25 times 10 to the negative 3 grams per 100 milliliter. I got that straight from here, all right, folks? Now, all I have to do is convert this to moles per liter. So I just tackled milliliters first. So I had 100 milliliters. To get rid of milliliters, I took 1,000 milliliters divided by 1 liter. And so that got rid of milliliters, and now my unit is liters, which is what I'm looking for. And then I have to get rid of grams. So 4.25 times 10 to the negative 3 grams. I went ahead and got the molar mass of PbSO4 on the side here. So 207.2 grams per mole of Pb, or lead, 32 grams per mole for sulfur, and 4 times 16 for oxygen. Altogether, I got 303.2. Okay, folks? And that's just going to be a review. I won't be doing that part for letter B, but I just want to throw it back there for a little bit. And then after I did my calculations, I did 4.25 times 10 to the negative 3 multiplied by 1,000, got that answer in my calculator, divided by 100, hit enter, and then divided by 303.2. I got 1.4 times 10 to the negative 4, and of course, since my units are moles per liter, then my units are therefore going to be molarity. So now that we have our concentration for the molar solubility, what does this actually mean? It means that 1 mole of this PbSO4 is going to dissolve into 1 mole of Pb2 plus ions and 1 mole of SO4 2 minus ions. Therefore, the concentrations of Pb2 plus and SO4 2 minus are also going to equal 1.40 times 10 to the negative 4 molar. And so all we need to do now is plug that into our Ksp expression. So now Ksp is going to equal to 1.4 times 10 to the negative 4 multiplied by 1.4 times 10 to the negative 4. When I put that in my calculator, I get 1.96 times 10 to the negative 8. I have the correct number of significant figures because they gave me 3 here. Now let's move on to letter B. So for letter B, we are given PbF2. It's a solid in equilibrium to dissolve to Pb2 plus ions and now 2 F minus ions. So everything is balanced. The Ksp expression is therefore going to be Pb2 plus multiplied by F minus raised to a power of 2. So again, we were given solubility. It was a little bit easier than letter A because we're given grams per liter, so there's no need to convert twice. We only have to convert once. So we take our 0.64 grams divided by liters and multiply it by the molar mass. I got 245.2 grams of PbF2 for every 1 mole, and that gave me 2.6 times 10 to the negative 3 molar of that PbF2. Now, PbF2, 1 single mole of it has 1 mole of Pb2 plus ions and 2 moles of F minus ions. We're going to use this to get our concentrations that we can plug into our Ksp expression. So for Pb2 plus, the concentration is just going to simply equal 2.6 times 10 to the negative 3 because it's a 1-to-1 ratio here. But for F minus, it's going to equal 2 times 2.6 times 10 to the negative 3. When I multiply 2.6 times 10 to the negative 3 by 2, I get 5.2 times 10 to the negative 3 molar. Now I have my concentration that I can plug into my Ksp expression. So Ksp is going to equal, of course, this expression here. I'm now plugging in values. So Ksp is now going to equal 2.6 times 10 to the negative 3 multiplied by 5.2 times 10 to the negative 3 raised to a power of 2, or squared. That's equal to 2.6 times 10 to the negative 3 multiplied by 2.704 times 10 to the negative 5. When I multiply these two numbers together, I get my Ksp answer of 7.0 times 10 to the negative 8. Now for this particular question, they gave us 2 significant figures. So therefore, my answer is going to be 2 significant figures. And this is a 7, folks. All right, on to the next. So this example wants us to determine solubility from Ksp. And so let's read the question. Calcium hydroxide, which is flake lime, is a major component of mortar, plaster, and cement. And solutions of calcium hydroxide, which is CaOH2, are used in industry as a strong, inexpensive bait. Calculate the molar solubility of calcium hydroxide in water if the Ksp value is 6.5 times 10 to the negative 6. So of course, we're given a Ksp value, which is awesome. We can go ahead and get our Ksp expression. In order to get a Ksp expression, we must have a dissolution equation. So we'll go ahead and get our dissolution equation for calcium hydroxide. We'll get our Ksp expressions. And of course, we can use that to our advantage to do what? Use a Rice table to solve for the molar solubility. So let's go ahead and get it, folks. All right, so first things first, I know I have to use a dissolution equation, and I know I need a Rice table because we're trying to solve for the molar solubility, and this is the second way that we're using equilibrium problems, okay, folks? So I automatically set up my Rice table. Then I got my dissolution equation. Calcium hydroxide is a solid, so we know it's not going to be used in our Rice table. So it's going to dissolve into our calcium 2 plus ion and 2 OH minus ions. Now in a Rice table, of course, if we have our solid and we don't use it, we're only going to be left with products. Well, initially we have no product. So we're starting with 0, 0 here, and we know it's going to be plus X and then plus 2X because we have a 2 in front of the hydroxide ion here. Now then that's going to give us our equilibrium amounts, which will be X for Ca2 plus and 2X for OH minus. Again, this X value is going to be related to our molar solubility. We saw that, or at least we kind of set that up before. Okay, folks? Now our Ksp is going to be 6.5 times 10 to the negative 6. We can use that to our advantage if we had to make any assumptions. We're not making any assumptions here, so we move forward. Our Ksp is equal to Ca2 plus multiplied by OH minus squared. So that's going to equal to, once we plug our X values in, X times 2X squared. So then I'm going to take my squared and take 2 squared and then of course X squared, and I get 6.5 times 10 to the negative 6 is equal to X times 4X squared. That's going to give me 6.5 times 10 to the negative 6 is equal to 4X cubed. And now I'm going to solve for X. Okay, so I have 4X cubed is equal to 6.5 times 10 to the negative 6. I'm going to divide by 4, both sides. I'm left with X cubed is equal to, once I divide these two numbers, 1.625 times 10 to the negative 6. Next, I take the cube root of both sides. So when I take the cube root of a cube root, I'm going to be left with X. And when I take the cube root of 1.625 times 10 to the negative 6, I get X is equal to 1.2 times 10 to the negative 2 molar. Now, for the cube root, don't forget, you will have to use this little button here. For my calculator, this button is the same as the little hat symbol. Here's the hat symbol. So it's going to be basically if you press second and this little button, that's how you can take the cube root. For my calculator, once again, I press 3, then I hit second. So I hit 3, then I hit second, then I hit the little cube root button again. Okay? And of course, I just hit the answer after that, or you can just simply type in 1.625 times 10 to the negative 6. Now again, as soon as we have our X value, we know that's going to be related to our molar solubility. How can we verify that? We just go simply back to the Ksp value. Our calcium 2 plus here is directly related to molar solubility. We don't have to multiply it by 2 or anything. It's a one-to-one relationship, and so we can directly get it from that concentration. And that's it, folks. Let's continue on to the next concept.